So we've seen a couple ways of computing the determinant already, but we're going to look at another one now called cofactor expansion. And this one is useful theoretically and will also be useful for computations, especially when the entries of the matrix have variables. So for a square matrix A, we say the minor mij of the ijth entry is the determinant that you get by crossing out the ith row and the jth column from A. So you cross out the ith row and the jth column, you have a smaller matrix, one dimension down, and that determinant is called the minor. And then the corresponding cofactor is when we take the minor and we stick in front of it a negative sign or a positive sign, depending on the parity of I plus j. So if we look at -1 to the I plus j, that's just this checkerboard pattern of signs, positive and negative. And so we give each minor a corresponding sign for its cofactor. Then the determinant can be computed by cofactor expansion by expanding along any row, in which case we're looking at, here we've got I fixed, so the row is fixed, and then j is counting through the columns, or by expanding down any column. And in this case, j is fixed, so we're holding the column fixed, and then I is ticking down through the rows. Okay, so let's look at an example to see what this works out to in practice for an actual computation. So let's take, let's do a 4x4. We'll look at the determinant of A, where A is 2, 0, 1, 2, minus 4, 0, 3, 1, 0, 2, 6, -3, 1, minus 1, 0, 4. Okay, so there's our determinant that we're going to compute. And so we could do any row or column. So which one should we pick? Well, if we pick this one right here, then we have lots of zeros, and that'll make life simpler for the computation. So let's go with that one. So now the formula that we're looking at, so let's see, so we're going down a column, so right here, the formula says we look at the entry multiplied by the corresponding cofactor. So we have the entry 0 times the cofactor of, let's see, so we're in, now if you look up here on the matrix of signs, we are in this column right here. So we're going to be starting with a minus sign. And then we have the corresponding cofactor that you get from crossing out the first row, second column. Okay, so then looking at what's left, so that's these entries here and these entries right here. We have the submatrix minus 4, 3, 1, 0, 6, minus 3, 1, 0, 4. Okay, and let me just tidy that up a little there. And now we're going to look at the next term. So the next term is the one corresponding to this entry right here. So we're again going to have a 0 times, and then we look at which where we are in the grid over here, and we have this plus sign. So there's going to be a positive 1. And then we look at what we get by crossing out the second row, first column. And so we have, let's see, 2, 1, 2, 0, 6, minus 3, 1, 0, 4 as our minor. And then going to the next one, let's see, so we cross out the third row, second column, and so our entry here was a 2. So we have 2 times -1 for this position that we're in, times the one that we get 2, 1, 2, minus 4, 3, 1, 1, 0, 4. And then, let's see, so for our last entry, so it's this one here, and that was a what? That was a minus 1? Gosh, I've sort of drawn all over. Yeah, that was a minus 1. Okay. So we cross off this row and this column, and so we have a minus 1, and then we have our sign right here is a positive 1, and we have 2, 1, 2, minus 4, 3, 1, and then 0, 6, minus 3. Okay, and so those are all the things that we need to work out in order to figure out the determinant of A. So notice that the determinant of a 4 by 4 got changed into determinant of 3 by 3s. So in general, there would be four 3 by 3 determinants to compute, and then each one might have some coefficient in front of it, whatever. But so you can see that this rapidly becomes an unwieldy method for computation. So if you have, like a 6 by 6 matrix to take the determinant of, you probably don't want to use this method because you're going to have to compute 6 factorial type things, and that's going to be no fun. So let's go back to the example that we're currently looking at. So because of the 0 here and the 0 here, we don't actually have to compute any of this business. That all goes away. We just need to compute these two at the end. Okay, so let's work those out. Okay, so for this first one, whoops, I'm still on pink. For this first one here, let's see. So maybe I'll expand down the second column right here. So I'm going to have a 1 for my entry, a minus 1 because of my position, and then crossing out that row and column, I have minus 4, 1, 1, 4 as the matrix to work with. And then for the next one, I'm going to have entry of 3, sign of positive 1, and a 2 by 2 that looks like 2, 2, 1, 4. And then I have 0 times a minus 1 times subdeterminant with 2, 2, minus 4, 1. And so that one is also going to die. Don't need to worry about him. Instead, I've got, let's see, so negative sign times, let's see, so we've got minus 4 times 4 minus 1. So there's 17. And then we're adding on 3 times 8 minus 2. And so that's going to give me 35. And then for my next one, I've got, let's see, I will expand, here, let's do the third row. It's got a 0 in it, why not? So we've got 0 times positive 1 times 1, 2, 3, 1. And then that one we don't have to worry about. And then we've got 6 times my sign for this entry, which is minus 1. times the minor, which is 2, 2 minus 4, 1. And then I've got minus 3, positive 1, and 2, 1 minus 4, 3. Okay, so this is going to give me, see, so I've got minus 6, 2 minus negative 8, plus negative 3, 6 minus negative 4. And I didn't leave myself enough room. Whoa! And so that's going to give me a minus 90. So the determinant of A was, let's see, I had minus 2 times 35 plus negative 1 times minus 90, and so that gives me 20. So there's my answer for this determinant. So like I said, not super efficient, but still often helpful. So just for an example of how inefficient it is, if you had a 25 by 25 matrix, then using this method, it would take the fastest computer on the planet, which is like, you know, they operate in terms of like teraflops or something like that, millions or billions of operations per second. It would take geologic time for a computer like that to compute the determinant, whereas you could compute the same thing using row operations on the same computer in, like, I don't know, less than a second.